All right, so let me start my presentation. My name is Dongbo Min, at Ewha Women's University. And today I'm going to talk about self-evolving hardware intelligence from pre-training and model compression to GPU or the system optimization. As a matter of fact, this title is a title of group project that I'm doing with my faculty member. And I'm going to introduce a couple of the research work that I'm doing among the many projects, among the many research work, especially based on the computational efficiency. So as you know that computational efficiency is very important whenever we are deploy our deep learning model into the real world. This is why we are trying to improve the computational efficiency at the various aspects. Among them, I'm going to introduce the three parts. And first part is I'm going to talk about what is that? This one. Efficient transfer learning from pre-trained model using parameter efficient transfer learning. And second part, I'm going to talk about compact network design using for network compression, using the quantization. And in the part three, I'm going to talk about efficient design for the GPU tensor core using the very effective data loading technique. Okay, so let me start with the part one. And this paper title is Dual Path Adaptation from Image to Video Transformer. And this paper appeared in CVPR, and this year's CVPR. And motivation is this one. So the parameter efficient transfer learning, which is also known as parameter efficient fine tuning, is becoming the popular as a very attractive solution to transferring the pre-trained model's knowledge into the new task. Let's say for instance, this technique was appeared in the NLP society in the beginning, but now it is being adapted into the computer vision society. And first paper in the vision community is visual prompt tuning in ECCB 2022, the last year. The idea is very simple. Let's say we have the pre-trained model, which is being frozen during our training, and we want to just add a learnable token as input. And then let's do some fine tuning, and then you can just tune this learnable parameter only, without doing any backpropagation into this part from the pre-trained model. So this is why we can do this fine tuning very parameter efficient way. So this is a part of the paper. And another way is that parallel or the serial adapter. Let's add some adapter in a parallel way or the serial way. And then let's do some fine tuning. And then we can only do some backpropagation into this part so that we can do the fine tuning very efficiently, only for the few number of the parameter in the whole the deep learning model. So this is just some couple of the paper that about this research work. And then, so here we have some couple of the motivation. So for instance, can we leverage the pre-trained image model for the video understanding? For instance, previous work just focus on, okay, we have a pre-trained image model, and what about using this pre-trained image model into the image recognition task? Something like, for instance, including the image classification or segmentation or the object detection. But what we want to do is that, can we do the video understanding task using the pre-trained image model? So I want to leverage some of the knowledge from pre-trained image model into the video understanding task. So by doing so, we can transfer the parameter of the image foundation model into the video domain, and we can achieve the comparable performance to the video model with only small amount of the learnable parameter. That's our motivation. So we want to do parameter efficient image to video transfer learning. So this paper appeared in CVPR this year, and this is a title. Okay, so let me introduce the overall architecture of this paper. So this paper, we propose to use dual path design for two-stream architecture for 3D video understanding. So we have a two-path adaptation for the spatial and temporal modeling. First one is a spatial path, and second one is temporal path adaptation. So this is some overall architecture. So we have some input video. From input video, let's do some adaptation from the spatial perspective. So this TS is number of the sample from the video. Let's apply some serial path adaptation for the number into the input frame. And then let's do some average pooling, and then let's do some concatenation. And then we have another path, which is called temporal path. So let's say this is some multiple number of image, and we just make it as a single image, and then let's do the temporal path adaptation. And then we have the picture map. It will be concatenated with the spatial path picture. and then let's do some classifier. Idea is very simple. So we have some temporal path adaptation, which is based on the serial adapter. We have a spatial path adaptation, which is based on the parallel adapter. So let me give you more detail about this paper. So we are transferring the powerful spatial context modeling of image model to the video data using parallel adapter. For instance, these layer normalization or multi-head attention or the layer normalization MLP, they are all the version during our adaptation. And then we just add a parallel adapter, here and here and here, and then let's apply this operation the multiple time. L is the number of the layer in the transform architecture. So this is the spatial path adaptation using the parallel adapter. Then let's apply the temporal path adaptation. So we want to learn the relation between the local path across the frame. So let's say we have this 4 frame, and let's generate a grid-like frame set. And then from this input image, this is just like a single input. And then let's apply the same architecture of the transformer, layer normalization, and multi-head attention. And then we want to add a serial adapter in between the two architecture. And then let's apply the backpropagation for this adapter while these components are being frozen during the optimization. So we are applying the serial adapter using the temporal context modeling. Okay. So let me take a look at let me introduce the quality. The result from this paper. So for instance, if you take a look at this one, this is some full fine-tuning technique, and their model parameter is, for instance, 420 million data, 420 million, or trainable parameter also is the same, because they are doing the full fine-tuning. So the accuracy is, for instance, 87.1 or 97.6. Surprisingly, using the parameter efficient transfer learning, our learnable parameter is much smaller. For instance, half, only the 10% or the 5%. And then we can achieve even better accuracy compared to this fine-tuning. So this is very interesting, the observation. This is very different from the NLP society. In the NLP society, they always mention that parameter efficient tuning is always less than, always inferior to the full fine-tuning. The full fine-tuning is some kind of upper bound of the parameter efficient tuning in the NLP society. But when it comes to the vision society, many people report that even fine-tuning, parameter efficient fine-tuning is much better than the full fine-tuning in some application. So we don't know why, but we may have to do some investigation why parameter efficient tuning is working better than full fine-tuning. That's what we have to understand in the future. Okay, let me continue to talk about. So here we have some parameter efficient tuning technique. So for instance, this is just, for instance, 73.3 or 94.1. We are comparable. For instance, 70.2, 72.2 or 93.7. So if you take a look at each one, the learnable parameter is much smaller, right? And then let's take a look at the attention from the data set. So this is for instance, if you take a look at this one, for instance, this one is attention from the temporal adaptation and attention from spatial adaptation. So here we are pushing the something so that it falls off the table. So here, if you take a look at, so this is a hand, to push the something, and then we can take some temporal, from the temporal adaptation, we can take some high attention for this moving the hand during our adaptation. So this means what you want to say is that using this adaptation, we can focus on the very highly relevant part from the input data. Okay, so let me continue to talk about the part 2, network quantization. So network quantization its goal is to reduce the bit width of the weight-award activation. For instance, from originally we have to use a 32-bit, we can reduce it up to the 8-bit, for instance. So we want to maintain each performance, accuracy, while using only the 8-bit. This is called the network quantization. And this network quantization is very popular, and there are two representative methods. First one is quantization-aware training, and second part is post-training quantization. So quantization-aware training, QAT, integrate quantization within the training. This is why it requires entire training sample for quantization. So this left figure indicate and represent QAT. For instance, we have an entire training data set. We have an original activation map. Let's apply quantizer. And then we have a low bit activation and each corresponding low bit weight. And then we can get some low bit network. So in order to do this training, we have to use entire training data set, even for the quantization. But when it comes to the post-quantization and post-training quantization, it calibrates quantization parameter from pre-trained full precision model so that we can get faster quantization of model compared to the QAT. So for instance, we have a pre-trained 32-bit network. Let's take only few training data set. We don't have to use any entire the training data set. We only use few training data set. Let's apply the quantizer, and then let's do some kind of the fine-tuning. This is conceptually very similar to the previous one, parameter efficient fine-tuning, but here we want to do training data efficient the quantization. So this is more effective in the real scenario. This is why the research work has been moving into the post-training quantization. Okay, so here we are doing the post-training quantization even for Bayesian transformer. This paper is going to be submitted into the next conference. So what we want to do is that we observe some very interesting phenomena. For instance, when we do the quantization, when we apply quantization to the Bayesian transformer, we found very interesting phenomena. If you take a look at these two figures, the left figure, X index is X dimension is a channel index. For instance, channel index for the single image. So what we observed from this figure is that the activation value in VIT has a significant scale variance across the channel, even for the single image. For instance, the 300 channel, 600 or 610 or 612, their variance is completely different, even for the single image. And the second observation is that the distribution of the activation for each channel changes dramatically for individual input data at the specific channel. So this X is the input data. For instance, first input, first image, and second or third. And then we are just visualizing activation range for specific channel. So even for the specific channel, for the specific channel, according to the input data, their activation map is varying substantially. This is why quantizing VIT is very much challenging compared to the convolution neural net. So in order to handle this problem, we propose the split quantization across, this is called split quantization across the channel. So what we want to do is that we split the channel of activation map into the G1s group. So let's group them. So previously, many papers just want to do the some quantization for the all channel at the same time. They don't do any grouping. But here, what you want to do is that according to the previous observation that we get, we want to group them, and then let's do the quantization for each group individually. That's our key motivation. But I'm not going to talk about technical detail about that. But finally, after grouping them, in order to group the channel into the three group, we are doing expectation and maximization algorithm. So we want to optimize UI and Li, and U and I is low upper bound and lower bound of quantizer, and I is index of group. So let's say we have for instance, 64 channel, and then let's group them, for instance, 4 group, and first group or second or third or the fourth. Then we want to do the quantization for each group individually. And in order to do this one, for instance, this left part is some expectation and right part is some kind of maximization process. So in the beginning, for channel C, please find what the phrase find some membership, which group you are belonging to. Afterward, for each group, let's find optimal upper bound and lower bound of each group using this energy minimization. And this objective function is max xc and upper bound and minimum xc minus lower bound. And this distance function, we can find this one. And this is not something like the learning process. This is just like some simple optimization using expectation and maximization. So anyway, key idea is that let's do the quantization for each channel individually. But if you do some quantization for each channel, this is too much time. Each complexity becomes too much huge. So this is why let's do the grouping. For instance, 64 channel, let's group them onto the 4 channel, a 4 group. And then let's apply quantization for each group individually. That's the key idea of this paper. Okay, so let me show some couple of the results. So for instance, we apply this technique into the image classification task. And this is a full precision using the 32-bit. And this is our technique. And if you take a look at this one, group 8 and group 16 and upper bound means we are doing the individual, we are applying the quantization for each channel. Obviously, this is going to be this will return the best result. So this is why we call this upper bound. But if you do some grouping at 8 or 16, and 16 already achieved a quite good result compared to the previous quantization technique applied for the VIT. So if you take a look at this one, 56 is 73. There is a big gap between the previous technique and our technique. The reason is that, as I talked to you, Bayesian transformer must be treated in a different way for doing the quantization, different from the convolution neural net. Okay, then let me continue to talk about the last item, the interrupt register reuse for GPU tensor. So here, many of you are not familiar with this one. If you are working on the Bayesian or the NLP problem, so this is more like more for the computer architecture. So this paper appeared in the PACT, which is a top-tier conference in the computer architecture. So let me give you some couple of the basic definition of this paper. So we have to, sorry for that. General matrix to matrix multiplication, which is called the GEMS, is commonly used in the convolution neural net or the LSTM or even in the transformer. This is, and in order to implement the GEM, GEMM, we can define the tensor core. And tensor core is the implementation, architecture, the format for implementing the GEMM. So for instance, what we want to do is that, let's say we have A multiplied by B plus C. Actually, many architecture, including the convolution neural net or transformer, is just nothing but matrix to matrix multiplication, just linear algebra, right? So what you want to do is that, for instance, the problem is that learning the neural net with the tensor core has some problem. The problem is that GEMM size is 100 times larger than the tensor core supported in our machine. For instance, we have to apply, for instance, 512 by 512 by 512. But tensor core just supports up to the 32 by 8 by 16. So this is why we have to apply multi-thread block and warping. So this means we have to partition the GEMM into the sub-block. So that's the real implementation using the tensor core. So let me give you some more detail about this one. So actually, GEMM, it must be decomposed, divided into the TB GEMM. TB here is the threaded block. For instance, let's do this one. For instance, input is 512 by 512, and we want to do the matrix multiplication of A and B. And then we won't be able to deal with this problem and this matrix multiplication due to the limit of the size of tensor core. This is why we have to divide this one into the TB gem. So for instance, if you take a look at this one, in order to calculate the C0, we are taking the D0 and D column. And then let's put this one into the TBGEMM. This means then we can reduce each size up to the 128 by 128 by 512. 512 is a channel size. And then afterwards, let's divide more once again. So which is called warp GEMM. So for instance, for this is the first warp. For instance, in order to calculate C00, we are taking these region and these region. So what I want to say is that in order to compute C00, the warp 0 is this one, C00, we are taking A00 and B00. And in order to calculate the warp 4, this one, we have to take out A00 and B02. The problem happened at this side. For instance, A00 is stored multiple times in the register file. So for instance, in order to calculate this one, the C00, we are taking A00. In order to calculate C04, we have to take out A00 and B02. So A00 is stored multiple times in the register file. So this is why the data duplication occurs in the same processing unit for the different verb that has their own register set. So this linker doesn't cover the problem. This is why we propose a new technique which is called interpret, and we modify the GPU architecture by using which is called register renaming. I mean, ideally it's very simple. Rather than loading the redundant data from multiple times, just to use a register ID, which is very similar to the point address. Rather than loading the data into the register, let's just use each address rather than calling. So, for instance, if you take a look at this one, for instance, for A00 and B00, we are taking out alpha into the register. And second time, in order to calculate this one, we are taking this alpha and gamma once again into the register. But we want to avoid this kind of the dual, redundant data loading into the register file by using register renaming. Rather than loading this alpha, we just take out each address and then let's take it out in order to compute this region. So by doing so, we can, this becomes empty. Then we can take out another, we can take out that. So alpha is not loaded multiple times. And then this is blank. So this allows us to preload on next input data. Idea looks very simple, but whenever we are doing some matrix and two matrix multiplication in the tensor core, there is some duplicate in terms of the data loading. So we want to avoid this problem. By doing so, this proposed method achieved the average speed up of 34% and reduce energy consumption by 27.9% compared to the baseline. And let me compare this technique with the prior work, which I, for instance, WIR and Diplo. And in general, interpret yields superior performance compared to the both technique, even using such a simple data preloading technique. So this is a proposed method, and this is a two paper appeared in HPCA 2018 and Micro in 2020. Okay, so let me end up today's lecture. So in this talk, I introduced several research achievements that we have done in terms of the network acceleration. In the part one, we propose how to train much more efficient way using parameter efficient transfer learning. This is from the software perspective. In the part two, we introduce compact network design using network quantization. This is also from the software perspective. And in the part three, we propose new data loading technique for better GPU core design. And this is from the hardware perspective. So obviously, the next step is naturally heading to how to design deep learning architecture from both software and hardware perspective. Actually, up to now, we are just working individually, but now is the time to combine how to design the better deep learning architecture. In terms of the computational complexity from the both software side and hardware side. That's what we want to do in this project. Okay, thank you for listening.
Thank you very much for your talk. We'll take a few questions from the clouds. So, any questions? Okay.
Thank you. Thank you for the very inspiring talk. I have a question on the dual path adaptation work. So using the dual path adaptation is great idea. I think it works quite well. Very small number of fine-tuned parameters on static bias data sets, such as kinetics UCF.
Yeah. Can I?
Because it is built upon a strong image model like CLAPE, so it's natural to add small number of parameters on top of it and only fine-tune those new parameters. But it might not work well on the dataset where you need some temporal reasoning, such as something. So can you share some results or thoughts on this? Like maybe should we design a novel adapter architecture for temporal reasoning?
Yeah, that's a very good question. So actually here we just apply very simple the modification in order to apply. I mean, the key idea is that we can do some special path adaptation using the pre-trained image model. But when it comes to the temporal path adaptation, we have a multiple number of the input data. Which if you just add this one into the image model, pre-trained image model, it is not the working, right? This is why we are using grid-like a frame set, and then in this case, one of the problem is that we have to know that their order. So in order to do this thing, we add 3D position encoding. So this is a key idea actually. If you don't have a 3D position encoding, it is not working actually. So this is one of the tricks to handle the multiple input data into the pre-trained image model. So we may find a better way to deal with these problems. So actually, this is a still open question. How to handle the multiple number of the input data into the pre-trained image model as input, right?
I see. Thank you.
I have a question regarding the second part of the talk on quantization, right?
Yeah.
So you mentioned these two methods, which both require some training data
Right, yeah.
for doing the quantizer in a sort of optimal way. I was wondering, could you do away with the training data completely and have sort of a teacher-student network set up where teacher network is the full network without quantization, student could be the quantized network, and then compare on unlabeled data, the outputs. Is that also something that is done sometimes?
Yeah, it is also possible. I mean, you are talking about something knowledge distillation. We have some the teacher model, and then I want to translate, I want to distill some knowledge from the teacher, and then I want to deliver this one into the student model. This is called knowledge distillation, but one of the problem in the knowledge distillation is that we still need a full training data set for training the student model. For instance, we have a teacher and we have a student. We need to add we need to use the same input into the teacher and student at the same time. And then we want to take out from the teacher from the teacher model, and then let's take out and then let's add this one into the student model. This is why there are few number of techniques, for instance, source-free knowledge distillation, but this is very early stage. So in the conventional way of using the knowledge distillation, they still need to use entire the training data set. So that's the problem. But here we only use a few number of the training data set. That's one of the main advantage of using this post-training quantization. I don't know my answer is correct for your question. Yeah.
Okay, maybe we can talk more later.
Yeah.
Thank you.
All right. Yeah.